until this point in the course, we've only talked about point estimation. So in other words, we've collected some data, we're trying to learn something about our parameter, and we've said we only want to guess a single point. Now we're talking about if we want to guess an interval. So again, we've collected some data, and now we're wondering what values of this parameter are believable given the data that we have collected. All right, so first let's talk about interval estimation for a mean, so mu. So in this case, let's say that we have data y1 through yn. It's a random sample, IID, from a distribution that's normal with mean mu and variance sigma squared. So let's have mu be unknown because we're trying to do interval estimation for mu. And for now, we'll say sigma squared is known. So this might not be very realistic, but that's okay. It'll simplify things just so that we can introduce this topic of interval estimation. All right, so mu is unknown, sigma squared is known. And so again, we're looking for an interval so that we can say which values of mu are believable given the data that we have collected. All right, so what we're going to do is think about our estimator. So our estimator might be our MLE. So remember, our MLE for mu is y bar, which is just the sum of the y's divided by n. So we need to think about what is the probabilistic behavior of this estimator. So in other words, we know that these y's are random variables, they have a distribution, and since all the y's are random variables and have a distribution, that must mean that y bar is also a random variable, and it must also have a distribution. All right, so we need to think about the distribution of y bar. Well, we know that y bar minus mu over sigma divided by root n is standard normal. And this is what we're going to use going forward. All right, so y bar minus mu divided by the standard error, which is sigma over root n, that's normally distributed, mean 0, standard deviation 1. All right, so maybe here's our standard normal distribution. And if we're taking samples of size n over and over and calculating y bar and then calculating y bar minus mu divided by sigma over root n, then we'd be getting values according to this distribution. All right, so we're interested in this probabilistic behavior of y bar. So let's think about what a 95% confidence interval would look like. So 95%, because that's what we often use in in applied stats courses, but we can talk about whatever level of confidence we want. But if we're doing a 95% confidence interval, then let's talk about 95. So we'd want to have it so that we have 95% in the middle of this standard normal distribution, and then 5% split evenly between the two tails. And we're looking for what this cutoff is. So that we have 0.025 in that tail and 0.025 in this tail. So we could go to a table, or we could use the pnorm command in R, and we'd figure out that this is equal to negative 1.96 and positive 1.96. All right, so we'll be using that later. Okay, so if we want to have a 95% confidence interval for mu, we look at those 95% cutoffs, negative 1.96 to positive 1.96, and so then we know that the probability that y bar minus mu over sigma over root n is between negative 1.96 and positive 1.96 is 95%. Because that's how we set it up, we chose 95%, then went and looked for these cutoffs that we got 95% in the middle Okay, so the probability that y bar minus mu over sigma over root n is between negative 1.96 and positive 1.96 is set up to be intentionally 0.95. Okay, let's look more at this. So sigma, constant. Root n is constant. Mu, we're back in the world of frequentist, so mu is a constant. The only random thing is this y bar. All right, so what we're going to do now is start to rearrange what's inside the probability here. So maybe we could start off by moving sigma divided by root n over. Okay, so we're trying to get actually mu all by itself, and so that we can create an interval, hopefully around mu. So then that means that our probability is going to become y bar minus 1.96 sigma over root n. All right, so we've rewritten this now so that we have mu in the middle, and we've created a random interval around mu. So our random interval goes from y bar minus 1.96 sigma over root n up to y bar plus 1.96 sigma over root n. All right, so here's one end of the interval, here's the other end of the interval, and the probability that this interval is going to cover mu is 0.95. So again, let's just reinforce this. Mu is constant. The random thing that's jumping around is the interval with one endpoint here, one endpoint here. So the probability that this random interval hits mu is 0.95. So we can think about, like, here's this unknown mu. One of our intervals might be here so that it would hit mu. Another random interval might hit mu like this, another one might hit it like this, another one might hit it like this. 95% of these random intervals are going to hit mu, they're going to contain mu, and 5% of these random intervals are not going to contain mu. So again, mu is constant, the interval is what's random, and so 95% of these confidence intervals are going to hit mu, contain mu, and the other 5% are not going to contain mu. All right, so let's just write down what the confidence interval is. So we have this random interval, which is y bar plus or minus 1.96 times sigma over root n. And that random interval is a 95% confidence interval for our parameter mu. So again, remember what we learned in applied stat classes. 95% of confidence intervals formed in this way will contain mu, and then 5% will not. We can never know when we're doing this in practice whether our particular confidence interval contains mu or not. All we can know is that if we do this over and over again, which we probably will because we're statisticians, then 95% of confidence intervals, 95% of 95% confidence intervals will contain the true mean, and 5% of these confidence intervals will not contain the true mean. So maybe this is comforting to you because 95% is a pretty good chance, or maybe it's not comforting to you because 5% of the time you're going to be creating confidence intervals that do not contain the true mean, and you won't know when it's happening. All right, so when you're actually doing this in practice, what you do is just go ahead and plug in your numbers. So you'd plug in your particular y bar based on whatever data you've collected. You'd plug in your sample size. You'd plug in this known sigma. So for example, if we had a sample of size 4 with numbers 6.5, 9.2, 9.9, and 12.4, and say that sigma equals 0.8, then our 95% confidence interval would go from 8.72 up to 10.28. So then we're 95% confident that mu is between 8.72 and 10.28. Again, we don't know whether this particular confidence interval actually contains our unknown parameter mu, but we know that if we went out and collected samples of size 4 over and over and over and over again, 95% of these 95% confidence intervals would contain the true mean. All right, so all of this is using the 95% level of confidence. If you want a different level of confidence, all we have to do is go back to this normal distribution. So say instead of 95%, you wanted just a general level, 1 minus alpha as your level of confidence. Then that means you'd have alpha over 2 in this tail, and we'd have alpha over 2 in that tail. And so we would be looking for these two cutoffs, so that we'd have alpha over 2 in that tail, alpha over 2 in that tail. And since it's a normal distribution and it's centered around 0, we know that this particular cutoff is going to be the negative of that cutoff. So we only really need to find one in order to do this. So all we need to do is use like a table or the pnorm command in R in order to find, the qnorm command in R to find these two cutoffs.